Christopher Fonnesbeck. He's an assistant professor in the Department of Biostatistics at the Vanderbilt University School of Medicine. And he specializes in computational statistics, Bayesian methods, meta-analysis, and applied decision analysis. And he's going to give a tutorial about a very hot topic nowadays, which is statistical data analysis in Python. So, all yours.
Thank you.
You want maybe?
Yeah, maybe stick it.
Yes.
Keep my hands free.
Yeah.
Great. Thanks a lot. All right. Try to stick close to the microphone here. Thanks everybody for attending the fourth tutorial. I guess I sort of dread doing the second or the fourth tutorial in the afternoon on the second day. Have you guys got anything left in the tank? I've been here before, so I've done 4 tutorials, and I know how that feels. So Frances has told me we've got about a half an hour for breaks, and I'll try to intersperse those pretty liberally to get you out of your chairs and keep you from falling asleep. So this course is it's sort of a mislabeled course in a way, because I think the reason that a lot of you are here is for pandas, and a lot of this course is going to be related to pandas, and really I'll follow a lot of the content of the book, but my particular spin on it is statistical data analysis, not just the more general data analysis. So what we mean by statistical analysis is applying statistical models to your data. And I think when Wes was here last year, he did a time series 1 or something like that. So every time he gives it a little spin in a different direction. So I'm going to do my best to give you a pretty good foundation in pandas, and in particular why we might want to use it in statistical analyses. So just so I get a kind of an idea of who's here, are there any actual statisticians here that have like a bachelor's or a graduate degree in statistics? Okay, a couple people. How many of you have taken at least one of these preliminary these intro level courses like the Numpy and the Matplotlib and stuff? Okay, most of you. And any R users here? All right, I'll try not to be too cruel. R is actually a pretty good place to start. I'm a statistician and a biologist, and I work in a department, Vanderbilt Department of Biostatistics, that is pretty much an R shop. Okay, Frank Harrell is my department chair. He's big in the R world, and R is a very, very good tool. But there's a lot of reasons that you might want to use Python instead of R, and it will generally depend on what you're doing with it, what type of statistical analysis. To say that a language is good for statistics is like saying a knife is good for cooking. Well, what kind of cooking, right? It's the same idea. So there are ways in which Python can be better than R. In particular, its performance tends to be better on average, though you can do things to make R faster, just like you can with Python. In fact, last year, we did a little, we actually hosted the Use R conference in Nashville, and a couple of us did a special session. Dirk Edelbutel and myself and Doug Bates did a little shootout between Python, Julia, and R for doing some statistical stuff, and R does pretty poorly. This was doing what's called a Gibbs sampler, which involves a lot of loops, right? A lot of for you iterate over and over again, sampling from a posterior distribution. R is just not good for loops, so maybe it's not fair. It's not playing to the strength of R, because R does have a lot of strengths. In addition, the R language itself is a little bit janky. And a lot of people don't like the way that it works. There's kind of a schism in R. There's an object-oriented version and kind of a one that relies more on conventions for objects. And now that we have pandas, data structures is a reason to use Python. It used not to be. You sort of wanted to avoid it, and R has really good data structures, but I think now the tide may have turned. And then, of course, IPython, which is gaining in popularity and is one of the tools that I used most often. So just to give you, sort of some motivating examples of statistical analyses using Python. These are actual analyses that I've done in the medical school at Vanderbilt and elsewhere, and it really shows how you can use a lot of these tools together, particularly if you're generating reports. When you're collaborating with people who aren't computer scientists or statisticians or data analysts. So here's an analysis. This is a meta-analysis of interventions for pregnant women to quit smoking and how effective they are. And you can do all your data importation into Pandas in the same spot. Lots and lots of data cleaning. Everything's annotated, so you can hand this off to somebody who's not computer literate, not statistically literate, and they'll be able to go back and see what you've done to their data and haven't butchered it too badly and so on. And then summarize things, and then generate plots and analyses and ultimately some results, some estimates, all in the same place. Similarly here, this is a really big analysis of the effects of different interventions on children with hearing loss. So they get ear implants, different kinds of hearing implants, and what those effects of those interventions are on their learning abilities. And this is a huge data set that have different components, and it involves a ton of cleaning that was all done in Pandas. And then these data sets were merged, and then we visualize components of the data by generating histograms, and then ultimately an analysis as well, a fully Bayesian analysis where we're estimating the effects of different components of these interventions, and we see the effects of hearing aids, of being male, of how old you are, and so on. Again, all in the same spot. Yeah. Okay, the question was, do people ask for this being they don't ask for IPython notebooks, certainly. They don't know what they are, but they always want reports. And in the absence of reports, the R community's got RStudio and Sweave and Knitter, which are really good for those sorts of things, but they're not really fully editable and interactive the way this is. So much like when I tell people they should be using Python instead of R for data analysis, it's one of those things that you got to show them rather than tell them about it. So I'm dealing with doctors and epidemiologists, and they don't know. They just see a report. They have a PDF file. They don't care about any of it, other than the fact that I can go in front of them and rerun the model with something, if they spot a mistake, and they like that sort of thing. So do people ask for it? Not in specific terms, but.
So how do you turn this into a PDF?
Oh, well, this is an IPython session, but there's a IPython, and part of the IPython project is there's a utility function called nbconvert, notebook convert, and you can convert it to LaTeX, which can then become this, or not this, but a PDF, as well as a bunch of other formats. You can turn it into a Python script too, and strip all of the notebooky stuff away. So just you can do really good analyses, statistical analyses using Python. And by the way, do interrupt with questions. Apparently we have time for questions at the end, but it's much better if you interrupt. So in terms of what you need, I've set up a Git repo on GitHub. You just go to my account. Hopefully you've pulled all this down already, but it really just consists of 4 IPython notebooks, and then a whole bunch of data. So hopefully one of the things that'll be nice about this is that we're going to be using actual data, doing real analyses, not just some toy examples. And so that's what's in the data section. So I probably should have, looking at other people's materials from other courses, I probably should have broken them down into more than 4 components, but because these get kind of big. But the first section will just be a quick, rather extensive introduction to pandas, the basics. I'm not going to assume that you've ever seen pandas before. And then what we would call data wrangling with pandas. So once you've learned the basics, how do you do real-world data manipulation with it? And then the third is a little bit of plotting and visualization. How many of you took the Matplotlib course? Okay, quite a few of you. So Pandas relies on Matplotlib for its plotting, but it does a lot more high-level stuff that we'll see, and including some newer stuff that's really, really nice for data visualization. And then finally, this is really what the title of the course is, how you build statistical data models in Python, again, using some real examples, okay? And one of the reasons that I'm sort of tying pandas into statistical data analysis is that one of the really important components of doing a statistical analysis is the data manipulation, importation, cleaning. The actual analysis doesn't take very long. It's mostly messing with data, particularly with people that maintain data in sort of questionable formats and with perhaps not being trained as a database person, which is usually the case in the real world. So let's start with the first notebook here. And I've annotated things pretty well. And by the way, I have no idea how long this is going to take. I use IPython notebooks a lot, but I've actually never given a long talk with one. If it were slides, I'd know exactly how long things would take. But I think I've annotated things pretty well, such that if we don't get to everything, you can go ahead on your own and finish up. I'd rather not get through everything and take our time and understand it as opposed to blowing through it all. So if you are watching the clock, don't worry. We may not get to it all. And so if you haven't worked through notebooks before, you probably have in some of the other short courses, but the ones that I've saved, the versions that I've saved to the repo, I've sort of cleared of the results, and we'll just click through them, and you can go in and sort of part of the hands-on part of it is you can go in and play around with it a little bit. You don't have to follow exactly the way I'm doing it, but there are some explicit exercises at certain points, particularly towards the end, where we'll take some time and see what you can do with the stuff. Okay? Yeah. What kind of JavaScript problem? It's probably MathJax related. So there's a component of the notebook called MathJax that does math equations. So you may not be able to see the math equations. Does it just not load at all?
No, it loads, but it doesn't let me use it. So I just click yes.
I've never had that error. I don't know if somebody is proficient in IPython Wizard. Are you on Linux or Windows or Linux? See how far you get.
The browser issue, maybe?
Probably, if you have to try a different browser, maybe. I'm surprised there's only one problem. Oh, a couple, okay. From Pandas? Oh, Numpy. Have you used it? Oh, so Numpy, the Pandas was built against a different Numpy or something. Oh, okay.
So I had quite a bit of problems yesterday. I used Python 2.7 and 3.3 side by side. I ended up downloading Anaconda and dropped it into a user space folder, and then just did a couple of symlinks. So I have like iAnaconda and Anaconda, which corresponds to IPython and Python respectively. So instead of typing IPython notebook, I type iAnaconda notebook, and it loads it with the Anaconda binary and all the things that is extracted there. That has been dead simple. It hasn't
That's a fancy solution, yeah, if he can do that. If you're really desperate and don't want to mess around with it, I've also included, in the links to the titles here, I've included static rendered versions, so you can at least follow along. If you obviously wouldn't be able to do the interactive stuff, but hopefully folks having problems can work this out. Okay, so just to introduce you, let me hide some of these things here. I don't think we need the headers and stuff. All right. Pandas is, what it provides mainly is a set of data structures for doing a number of tasks. It's particularly good for sort of tabular data, so the things you get in spreadsheets, which is often the form in which you receive data. So you can import it from comma-separated values, SQL tables, Excel spreadsheets. Really good for time series data. Wes, the main developer of Pandas, is a financial guy, and so it's highly tuned to doing panel. In fact, the name Pandas comes from panel data analysis, Pandas. So really good for time series data, and in particular data with rows and columns in particular that aren't all the same type, which is troublesome outside of Pandas. So a lot of really useful features that we're going to touch on with varying degrees of detail in the course. One is that missing data is handled really well here, and that's not the case outside of Pandas generally. It's one of the strengths that R has. Okay, R was designed by a statistician for statisticians, and your real data is full of missing data, if that means anything. It has missing data or doesn't have data, and it's good at dealing with these. Also, really easy to mutate size, shape of data. Restructuring things is really easy. Data alignment, okay, when you're merging tables together, so some sort of SQL-like functionality, able to merge on indices and various columns. Group by functionality, what is informally called the split, apply, combine method for data analysis, is really easy in Pandas. Lots of slicing, indexing, subsetting, hierarchical labeling of axes, which we'll get to, and some really good I/O tools that make getting your data into and out of Python a lot easier than they would have just using Numpy or various tools like that. Okay. So yeah, the Pandas is sort of hosted. The homepage is on pydata.org. It's got excellent documentation. Also, the unit tests for Pandas are extremely good coverage. Wes is fastidious about this, so you can get a lot of the details there. I like to abbreviate, take advantage of namespaces here, so I'm going to use the PD convention for Pandas, so I'm importing the library as PD. And then first thing you'll want to do is tinker with the display options. And this is sort of morphed over the years, but right now the convention is this set option function, and you give the option that you want to set as a label and then its value. So I don't like having HTML output. I just want plain text output, so I set HTML to false. And then these just mess around with the number of rows and columns that get displayed before it tries to abbreviate things. And you'll get the feel for it and try to tinker with it yourself. So the data structures are really the core of Pandas, and there are two primary ones. The first is what's called a series. So a series is rather like a NumPy array, except that along with the values itself, there is also a corresponding vector of labels. And by default, if you don't give an index yourself explicitly, it just assigns a sequence of integers, ordered integers. And as you can see, just like a NumPy array, it's got a D type and so on. And so we got two attributes that are of interest here: the values, which is a NumPy array, and then the index, which has its own special class, an int64 index in this case. And one of the nice things is you can assign meaningful labels to your indices. So this is kind of fake. One of the data sets we'll see in here is a microbiome data set. So these are bacteria that they find in your various parts of your body. So we'll pretend these are counts from DNA or RNA sequencing, and these are different phyla, I think, of microorganisms. So we're going to use those labels instead of 0, 1, 2, 3, 4. And those labels are useful in that now you can access, you can refer to the values in the series by those names. And also a nice thing to do when you pass code over to a doctor or whoever you're collaborating with. So you can index things out just like you would a dict, right? You can give series, a list of indices, if you like. So what if we just want the ones here that end in the word bacteria? So we just do a little list comprehension, pull out those guys. And that's just because this ends up being a little list of booleans, just indexing like you would in a NumPy array. Of course, you're not forced to use the labels. You can use positional indexing as well. And we can even give the indices and the series itself labels. So we're going to call the index phylum, because that's what they are, phyla of organisms, and then we're going to call the name of the series itself counts, because these are counts of bacteria. Okay. Nice thing is you can apply things like NumPy's math functions. So we're dealing with things like bacteria that can vary in orders of magnitude. You might want to take the log. So all we have to do is np log, and lo and behold, we get back a series. Okay, it doesn't cast it to an array or to an array or anything like that. Pardon me? Oh, well, I haven't explicitly, but yes, sorry. You may want to go in. Right.
I fixed my problem with Pandas. It was dependent on NumPy 1.7.
Okay.
I hadn't ordered NumPy.
It's always fun installing packages with lots of dependencies. Yeah, sorry, I have in my IPython configuration, because I use it every time, I just load it. So sorry about that. I probably should have just used a plain one for this. But yeah, I might use a similar convention, import NumPy as NP. I think that's the only one I use explicitly in here, but I'm sure you'll let me know if that's not true. Where are we? Okay, yeah, we can use the value, just like an array, we can use the values to filter. So however many with counts more than 1,000 in this case. And what we can do is actually create series from a dict. So it's like a key value store, right? So create it as a dict and pass it to the series constructor, and we get a series. That's another way of creating a series rather than passing a list or something like that. I think it's an array internally, but the series will, there is a dict structure in there somewhere. Another disclaimer is I don't contribute to this project at all, so my knowledge of the internals is limited. I'm a biologist and a statistician. I'm not a computer scientist, but I should know some of these things. One really interesting thing here is that if we take that dictionary and we could pass it a custom index, we don't have to use the one in the dict. And in fact, here what I've done is I've included a label that actually isn't in the data. So I've gotten rid of proteobacteria and I've added cyanobacteria. And so what do we get? It's this. So there is no cyanobacteria in that original dictionary, and so it's not there. And there's no, which one did I get rid of from Q's? Bacteroides, sorry. So it aligns the index that I passed it with the index in the array, or in the dictionary, excuse me. Okay, and so what Pandas uses as its sort of missing data convention is this NaN, not a number. I avoid over-interpreting that. It's a placeholder for a missing data value as far as Pandas is concerned. So the nice thing is that these labels are what we use to align the data. So if I can add my original bacteria series to bacteria 2, and for the ones in which there's missing data in one series or the other, it becomes a missing value. You can't add a missing value to a non-missing value, you get another missing value. Okay. All right. So that's a series. That's kind of the one-dimensional equivalent of an array of, or a list in regular Python or NumPy. Data frames are why we came to Pandas, right? Come for the data frame, stay for the plots or something. This is why we use it, is this data frame. And it's modeled after, I believe, the R. It borrowed a lot of ideas from the R's data frame, which is extremely powerful. But Pandas data frame is even more powerful. And the reason we need it is because most of the time the data we get are multivariate. Okay? And so we have a set of variables all in one data structure that we want in one data structure. And those data can be of different types. We can have strings and integers and floats and what have you. And we want them to play well together. So a data frame is a tabular data structure that works not unlike a spreadsheet. Even though there are sort of only two fundamental dimensions, we have what's called hierarchical indexing that can allow us to create the illusion of multiple dimensions. You can view this as a multidimensional data structure if you like, at least in practice. Here's a simple toy example here, again using our fake microbiome example. And so here we've got some counts of bacteria, and then I'm giving it patient numbers. So these again came from parts of the body from different patients, and then those are the phyla. So now we have some couple integer valued columns, and then a string, just as a simple example. And what you notice right away actually is that the data frame is sorted by column name. So even though I passed it value, patient, phylum, dict is not ordered, right? It's an unordered set. It puts it in alphabetical order, but you can specify otherwise. In fact, if you want to reorder them, you can simply do this. So you can pass a list when a list is ordered, has an intrinsic order, and so this will just take that same data frame and rearrange it. Okay. Since we have two dimensions, we actually have two indices, at least two indices. So data, the columns have an index, patient, phylum, value. And notice it's not an int64 index anymore. It's just an index. And if we want to access those columns, we can do that using, again, the sort of dict-like indexing by name, or by attribute. Okay, so there's now an attribute called value. There's also an attribute called patient. These are all attributes as well as the dict structure. And when you do access these attributes, or index them out, they come back as a series, a single column. However, if we pass it, if we do an indexing as a data frame, so we give it a list with one element, it comes back as a data frame. Okay, so that it easily generalizes if there was more than one item on the list. So if you want a data frame back, you want to do it that way. What about rows? The way we access rows to distinguish it from accessing columns is we use this little indexing attribute, and we put square brackets around that. So if we want the third element here, actually the fourth one, and as far as we're concerned, we give it data.ix bracket 3. In terms of creating data frames, we can do it with a variety of ways. Addictive dicts, right? So row-wise, you might get data in row-wise. You want to add data, as you get it somehow. And so, but we probably want to transpose this. So DataFrame has a transpose method property, and can easily do that. Okay. One thing that's worth noting, and hopefully prevent you from making this mistake too often. I'm sure you'll do it anyway. But these indexed attributes series, these are actually just views to the data frame. So you got to be careful. Even though I assigned value data.value to a local variable called vals, if I set that to 0, and then I go back and look at my data frame, lo and behold, it's missing. It's been changed. Okay, and so of course we want to make a copy of that. So now if I assign that 1,000, it hasn't changed the original data frame. Okay, so those are just views. Be careful. Yes.
You say you transpose it. I mean, you're literally transposing data. Is that like a front transpose or a melt?
No, there is a melt function that we'll see later. Oh, sorry, yes. He wanted to know if what kind of a transpose this was. Is it like melt in R? No, it basically just taking the column index and making it a row index and vice versa. That's why it happens so fast. Yeah, yep. Of course, we can modify these rows or columns by assignment. So I just showed you how to do that. I'm not sure why I did it again. But you can add a column this way. So I want to add year, say these are all patients that were sampled in 2013, and so we assign it a scalar value, and it knows it's smart enough. It's very high level, okay? You can turn it into a column. However, we can't use the attribute indexing to create a new column, okay? So if I create treatment and I want it to be 1, it's not there. It doesn't know that they want this particular attribute to be a column, okay? The data structure has lots of attributes. Not all of them are columns in the data table. So all we've done is created an attribute that's 1, that's useless. And so what we have to do actually here is assign it using the dictionary style indexing here. And that's how we know it's meant to be data, okay? Right, and I just create a little fake series here. Notice that because I created a series, and that series has an index, and I use that, and I add that to or I append that, I concatenate that essentially to the data frame, it respects the indices, okay? So I purposely only had 6 elements in this column, and I'm adding it to a data frame with 8 rows, and so it did the right thing, created missing values there. That's super nice. You do have to be careful, though, because other Python data structures aren't treated as well. So if I just have a list, say I'm assigning months, and I only have 4 of them, I get an error there. It doesn't know what to do. So I've got to make sure that that list is of the right length. Okay. Or I could have just created a series if I really only wanted 4, just like I did before. Removing columns is easy. Again, just like deleting an attribute. We can extract this underlying data, and the underlying data is, lo and behold, a object-typed array, because we've got heterogeneous columns here. So obviously it blows away some of the typing, but it's going to cast as necessary whatever it takes to get it into the appropriate type of an array. So here I've got some integers and some floats, and it made it df.values ends up being an array of floats. Okay. So it doesn't automatically turn it into an object, which is nice. A little bit about this index data structure. Like I said, it has its own custom data structure, the index type, and there are several subtypes. These index objects are immutable, unlike the data columns themselves. So if I want to change the first index here to a 15, it doesn't work. And the reason that doesn't work is because we sometimes share these indices among data frames or data series, and you don't want a data frame over here that was relying on that index to be changed underneath it. So what we have to do is create a copy. See, we assign an index from one to the other. And if I wanted to change the index, I would have to create a sequence of numbers from 0 to 7, turn the first one into 15, and reassign it an entire index, as opposed to trying to mutate a single element of it. Okay. Importing data. So this is one of the things I always hated about doing data analysis before Pandas. I love Numpy, but I don't love load text. You have to do stuff like this in order to get data and specify types. You have to be very explicit. I really don't know what less than F4 means. I probably should, but I don't. So you have to go online and search for all this stuff. We don't want to do that. I don't want to do that. So Pandas makes a few more decisions for you, but generally does a better job. It's a matter of opinion. Some people maybe like the control that load text gives you, but I don't. So let's look at some of this data. This is a CSV file that contains, again, the taxon, patient number, and then the sample came, these are from little kids, and one came from a stomach resection, piece of the stomach tissue, and then other from poopy diapers. And those are the counts in each. And so Pandas has a whole series of read functions. Okay, whole bunch of them. We'll cover a few of them here. The one of interest right now is read_CSV, and we get this. And so notice it doesn't show me all of the data right off the bat, and that's because the way I have it, Pandas, or IPython and Pandas configured is that I'm only showing a maximum of, I think, what did I say, 20 or 30 rows. And there are 75 here. But it gives you a nice little summary of what you see. We know what its index is. We know how many non-null values there are. We know the types. It doesn't tell you which type corresponds to which column, but in this case, it's pretty easy to tell. But notice that it made that conversion. It knew that taxon was a string and everything else were integers, and it encoded them accordingly. What it also did is it interpreted the first row as a header. It knew that as well, which is nice. And we can override all these things. We can go in and say header equals none, and you'd never want to do this, but that's what it does, right? But sometimes we don't have a header row, right? Read CSV, of course, is just a convenience function for a more general function called read table, and we can give it any sort of separator that we want. We're probably familiar with seeing those sorts of things. And a nice one in particular is using a regular expression as a separator, because sometimes you'll have a varying amount of white space as a separator, right? If you get data that was used in some sort of Fortran analysis or something, and ragged-edged separators. And so all we're saying here, for those of you who don't know regular expressions, this is the expression for a space, and then the plus is one or more of them. Okay, so it does a pretty good job of that. We were given there are no index labels, so we can specify the labels of the different columns. So, here's what we're going to do here is we're going to create an index using the first two columns of the data set. So if we look at this data, unique entries are identified by the first two columns, right? So there's can't use firmicutes as an index, it's not unique. Can't use patient because, well, it's unique in this subset, but they're not unique in general. We see that they're repeated. And, but the combination of the two of them creates a unique index. And so we specify an index column. So I couldn't just give it one. I had to give it two in order for this to work properly. And so we even get a nice pre-printed version of this where it doesn't print firmicutes all the way down. It's firmicutes until it changes to another one. So if I put 20, you'll be able to see it here. There we go. The next one starts down here. And so that, I'll get into hierarchical indices a little bit later, but that's kind of a preview. Yes?
So going up a little bit, instead of printing out the summary on the table too large, can you enforce the data frame look of the data frame where it has D types and everything, but shows the table?
What is it that you want to see? You want to?
So I want to see the actual table instead of the summary.
Oh well, the way that you can do it is by adjusting.
Just for that.
Oh, just for that one?
Yeah, just for that one.
I imagine you could do it with like a context manager or something. I'm not sure. Yeah, just that one. I think you'd have to use a context manager for that, or set it and unset it. I usually just use a head, and so you can get a peek at it. So if you're using thousands of records, you're never going to want to see them.
Is there a way to get it quick through like statistical analysis, like a plot means or?
Yeah, there is. I'll get to that. Yeah.
So
Yes.
So you said it was pre-printed and it changed when that first column changed. So does that imply that it's sorted?
Yes. Correct.
So there must be a way to sort of which column?
You can re-index it. Yeah. We'll get into some of this stuff a little bit later. Some of this is just a preview for you. Let me see where if I can find where I left off here. Doop, 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 doop. Here we go. There we go. Okay. Lots of different customizations you can do. We can skip particular rows. So we're some invalid rows for some reason, or we can just specify the first four if we want to. Often you'll get a data file that's extremely large. You may not want to import it all in one go, so we can break it into chunks. So we know in this file that it comes in kind of chunks of 15. So each taxon was measured in each of 15 patients. And so we can break it up into chunk sizes of 15. And then what I'm going to do is take the mean of those chunks and make a little data frame, or sorry, just a dict in this case, out of that. So we can do some quick summarization of the data without keeping everything in memory. Like we said before, missing data is everywhere. So I just want to do a quick example of importing data with missing values. And so I just went in and changed some of these. And this is where you get different conventions by different people. So I did a few different ones. So NA is big. You get that in. That's kind of the R's standard placeholder. You can get things like a large negative number in a series that shouldn't have any negative values. Question mark. Some people just leave it blank. I think I've got that up here, and so on. And so if we just import it, we get. I did the right thing in two cases. It interpreted a empty space as a missing value, and it interpreted NA as missing value. However, we still see -9999, and we still see question mark. You get some bizarre stuff sometimes. And you can see that the ones that it identified as null, the pandas function called isNull if you want to see these things, and I'll sometimes just do a sum on that. and it will tell me how many missing values I've got. But here, of course, we want other values, and we can do that by specifying NA values. And so now when we keep hitting Shift instead of Enter, now we've appropriately identified all of the nans. And one really cool thing is that you can pass a dict to NA values and say, just look for question marks in tissue, just look for negative values in stool, etc. Okay, so you can specify them. Yeah.
What happened to the question mark? There's a character, then you have numerics. Took it like, it looks like a slide justifier.
Yeah, so up here, it would have turned this into an object type because there was still a question mark. So the question was, there was a question mark, what did it do to the type for that column? And in the one where we didn't specify question mark as an NA value, it had to convert the whole column into an object. But here, it didn't have to do that. And we can see that by getting rid of this. And so, yeah, the only object here is taxon, which is string. Everything else is either int or float. So missing values don't count against the type, in other words. Okay, so unfortunately, people mistake spreadsheets for databases and keep data on databases. We probably have them on our computer as we speak, right? Unfortunately, but we usually we have to deal with this. This is what people email you. So Pandas is equipped to deal with this. We do need a couple of external or third-party packages, that being XLRD for XLS files and OpenPyXL for XLSX files, so the newer version of Excel. And you can just do a pip or an easy install or what have you, or just skip this bit if you don't want to pollute your computer with Excel stuff. And so there's sort of a two-step process that's recently been combined, but we import this Excel file using Excel file, which creates this Excel file object. And then, of course, spreadsheets, you have to deal with sheets, right? Sorry, question?
Sorry, so when you enforce NA values, that turns that tissue from an int to float. Is there any way to not do that?
I'm not sure why I did that, actually, because I don't think I have any floating point. Oh, nan's a float. But wait, it didn't do it for tissue, though. It only did it for one. Oh, two. Oh, yeah, you're right. Yeah. I don't think so. Yeah, you're stuck with the type of the nan. Yeah. We can try. Hold on. Can we cast it? I wonder. Well, we'll deal with this later. I don't think so. Is the short answer to your question. Sorry, I'm generally looking over here at this screen because I don't like my screen all being squeezed up. So if you have a question back here and I don't see you, you can yell my name. I don't mind. So anyway, back to the Excel file. We have to deal with sheets, multiple sheets within a spreadsheet. So we then parse sheet one. And that's whatever name they've happened to give the sheet that you're interested in. And by default, I think in Excel it's sheet one. And in this case, there was no header, so we're going to give it columns some names. And lo and behold, we get this. This is slightly different data, by the way. It's specified all the way down to the genus. So it's big, long name here. We'll see more of that in a bit. There was recently a read Excel function that was added, which combines these two steps. So all you have to do is specify this sheet name, extra sheet name argument. Okay. And so this is sort of the tip of the iceberg because you can do all sorts of data like JSON, XML, HDF5, relational databases, and so on. In science, you don't get much JSON yet, at least maybe in genomics. But so I chose to do other ones. But the book, the Pandas book, goes into that, and there's really good online documentation. But didn't want to spend all the time on importing data. You get the idea, I think. Okay. So now that we have our data structures, we have data in those data structures. How do we mess around with them? So we're going to leave our digestive tracts behind and look at some baseball data. This data, I believe, actually ships with Pandas as well, but I took it out and put it in my directory also. This is just some batting data from 2 partial seasons, 2006, 2007. So baseball data is always good because there's lots of different data types, and it's fun. Everybody loves baseball. So here we identify, it's got an index column, so a unique identifier for that row. Each row contains a player's name, the year they played. Some players had more than one stint with a team, okay, or more than one stint with more than one team. So this guy here, Tio Womack, can't remember his first name, but his last name's Womack, played with 2 teams. So this is a Chicago stint. And then baseball stats. All right. We could make a more, even though we have a unique in it. Yes. You don't see the data when you.
I think it's transposable or something. Yeah.
What do you?
It's the other way around. What was the option to transpose it?
Just dot capital T. It's strange that would happen.
No, that's not that.
What do you got?
Even in the right spot, I get it.
Do you?
Yeah, sorry. Yeah, I was in the wrong. Yeah, I get this. So I've got all these names. Yeah, the right names. They get them down.
No, those are the columns. Oh, you just you've got different display options. So I set my display options. I set my display options up at the top to allow for like 30 columns, and I think the default is like 10 or 15. That's the only difference.
Yeah, we ran that.
Really?
Yeah.
That is why it's doing that. It doesn't like your. Could be. Yeah, if you're using an older version of Pandas, I think set options changes like weekly. So don't worry about this. Just I can't remember what it used to be. In fact, you can go in, you can tell. If you go. One of the nice things about the inline docs here is it actually tells you what your current setting is. And so number of columns and column line width I've set to, the default is 80, it's set to, so max columns I switched to 30 and it defaults to 20. So you can see what yours is set to. Is it the same? No. It's not critical that you have the same view as me, so I won't spend time on it.
Yeah, you just have to expand it even more. Actually, you just have to make those.
Make the brow, yeah. Yeah, mess around with it till it fits your. Right. So, sorry, what I wanted to do here is use a more meaningful, or implement a more meaningful index than a number. Because if I index out a row, or if I want to index out a row, I might want to know what player that I'm dealing with. And so what I'm going to do is create a series that's the player's name and then its year, right? And create an index with that. So I'm going to assign that player ID to index, and now we have this index here. Okay, now it looks all right, but if you can, there's an attribute called isUnique for any index, and it says false. And the reason that it's false is this variable here called stint, right? So Tony Womack, that was his name, Tony. Tony Womack played for two teams in 2006. He was traded. So we have to include that as well. And in fact, if we look at our series, there's a handy method called value counts that gives you a nice little summary of unique values and how many times they appear. And there's a whole bunch of players that were traded during the 2007 season. So you deal with those. But we can, just because an index is not unique, you can still use it. But if I index out Tony Womack in 2007, I get 2 entries. Okay, he was traded from my Atlanta Braves to the Arizona Diamondbacks. And so we'll look a little bit more about that later. But now all we have to do is add stint. So now it's, or what did I do? No, I added the team name, right? So as long as they didn't have 2 stints with the same team. So Womack, Tony, Chicago, and then there'll be another Tony Womack. And now if we look, it's a unique index, okay? If we care about such things. We had a question earlier about the ordering of indices. Indices are indeed ordered, and we can manipulate those using reindexing, okay? For example, if we want to simply reverse the order of the data set. So right now it's in order in I think, alphabetical order by year. So if we index it by ::-1, which means from the beginning to the end in reverse order, reverse steps, and we have a look at that, we get it backwards. So it starts at 2007 rather than 2006. Okay. All right. One thing we can also do, we notice here that even though there are these unique IDs for every player by year by stint, they're not sequential. There are some missing values in here. So say we wanted to, populate our table with every ID value and somehow fill those in. Who knows why we would want to do this? But what we can do is add a new index that is simply the range from the smallest value to the highest value. And so we create all these entire rows of missing data. But now we have this new index here that won't return an error, at least when we try to index it out. Missing values can be filled automatically if we want to. So we specify this method argument, and one of the options is forward fill. And so what it does is it will take the value in the previous row and fill it forward. And then bfill is backward fill, so it does the reverse. So if we do forward fill, just to say for two columns, just so everybody can see it. So now we've filled Tony Womack into this number, even though it didn't exist before. Who knows if that was him or not. Or we can create a custom value that might be more meaningful, right? Fill it with a particular value. Okay. The one time you do need your indices to be unique is when you use reindex. You won't know what to do if you have a non-unique index. So that's one thing to keep in mind. You usually want a unique one. Okay. We can easily remove rows and columns. Okay, so if we want to drop two rows for some reason, now we only have 98 rather than 100 players. Or, who needs to know about intentional base on balls or hit by pitch? Let's get rid of those columns, and lo and behold, those are gone. Okay, just using drop. But you got to specify axis equals 1. So axis equals 0 is the rows. Axis equals 1 is the columns. All right, we'll try to make it through this. We're just a little past an hour now, so give you a break after this. We've seen indexing already. It works a lot like Numpy, but with a few added ways of getting at your data. So what do we do here? Okay, it's just a sample series, so we just want the number of hits using our new index. And of course, we can take a slice out of that, take the first 3 values. We can take just 2 player years. Interestingly, because an index has an order, you can order from one index label to another index label. So we start at Tony Womack in 2001 with the Cubs, and we go all the way down to Luis Gonzalez in Arizona in 2006. And so that's, I think I only made a couple of, yeah. So it's a couple rows down. Okay, so if you know the beginning and end of the section you want to cut by name, you can do that. You can also assign values based on that slice as well. Very, very handy. In a data frame, if we're using a data frame rather than a series, we can slice along either or both axes. So we can take 2 columns, we can take a certain number of rows, so this is with at-bats greater than 500. But then we can also say, I want Luis Gonzalez, 2006 with Arizona, and just hit the ones related to his hitting. Or if we knew that it was, 5th to the 8th index and so on. So we're taking a slice here and then a list, or we can take the first 2, etc. Okay, just a few examples. There's another method that doesn't get used quite as often, but it's worth knowing about. And it's the cross-section method, XS. This isn't, unlike IX, this gets confusing, because IX is an attribute that you index like a dictionary. XS is a method. And this method will extract a row for you, okay, by label. And it returns it as a series. And generally, those will be objects because columns are of different types, right? Yes. Yes, I will. Correct. Yeah. Yes. Oh, damn it. I'll do it every time. XS doesn't return a view because it's not an attribute. It's a method that returns its own object. So you can mess with it. I can hold it, but then I can't use my... I wish I had a button on one, but... Do you want me to wander around? All right. Can do the Merv Griffin thing. All right. Section on operations. We can perform operations between Pandas data structures. So right here, I'm pulling out home runs in 2006. So I've indexed out, filtered out year equals 2006, and then I've taken all the home run. So here what I didn't show you, that I use this as an example, is XS on axis 1 pulls out the column. By default, it's axis equals 0. So I can use this cross-section method on any axis. Okay. So I'm doing that for 2006 and 2007. And what have I done down here? Oh yeah, I'm giving it a good index, and then I add them together, and this is this data alignment that I've been talking about. I think 2006 there's only like 5 or 6 players in the whole data set, and so the rest of them are not nans. And so when I add them to 2007 that has a lot more players, I get lots and lots of nan values. These are the only ones that aren't. So if I do home run total that's not null, it's just these 6 players. Okay, and so so we like the operation honoring this the data labels, but maybe we don't want the data, the missing data to be filled that way. Since it's a count, something like home runs, we could just add zeros, and so now players that have missing values on one or the other, they just substitute a 0, and that allows us to add 2006 and 2007. Okay? And that'll happen. Some players only played in one year or another. We can broadcast between rows and columns. So for example, I can subtract from home runs the player who hit the most home runs in that particular year. So I'm taking a series here, and I'm subtracting an integer value from that. And so we get a nice series that shows how much worse than the best home run hitter everybody did. Okay? Or you want to do things row-wise, we can look at a particular player. So this is Barry Bonds, all-time home run leader and cheater. And That's his name. So we might want to see how everybody did relative, to Barry Bonds. So we take all our stats of interest, sorry, hits, doubles. So this is hits, doubles, triples, and home runs, and we subtract from that Barry Bonds value, and we get everybody. So this guy did better than Barry Bonds. That wasn't his big year. This is Luis Gonzalez, because he had lots of doubles.
So could we add a column to the data, use steroids? Yes.
The question was, could we add a column to the data that labeled them as steroid users? That would make life a lot easier for Major League Baseball, but yes, we can. I don't know how to do that filter, though. Yeah, you'd assume they're yes until they send you blood samples. That's right. We'll model that later in the second part. We can apply functions to each column. So if we want the median value of any of these statistics, and then, so here's a lambda function that if we want to see what the range is for any set of statistics, we take the maximum minus the minimum and use the apply method. So the apply takes that function and applies it to every column or whatever axis that we apply it to. Yes?
So what if you have a NA and when you do that?
It does whatever your function does. So if max and min honor NAs, which I don't think they do, I think it'll NA the whole thing. So you will have to drop NAs or do something with them first, fill them, so on. Yeah. All right. So here's a quick example. Let's calculate some statistics. So one statistic that is often cited in baseball is slugging percentage. So you basically get a point for every base, right? So a single is 1 point, doubles 2, etc. You divide it by the number of at-bats, okay? And we're going to nicely format the resulting estimate. And so we have a little lambda function that does this calculation, and then I'm going to apply it to all the columns. And so we get our slugging percentage using that apply function. Okay. Sorting and ranking. So lots of useful methods here. Sort index simply sorts based on the index values, alphabetical or alphanumeric order. So we got our A's all the way down. If we do tail, of course, it would be down to the Z's. We can do ascending equals false if we want the other way around. So we start at the Z's and go up to the A's. Or we can sort along the other axis. So now we sort from column-wise, noticing that capital values get counted before lowercase values. So that's why X is first, because it's capital X, and then A, B, C, etc. Order does something slightly different. It sorts a series by value rather than by label. Okay, so these are the ordered home runs. So the most home runs hit was 35, and obviously the fewest are 0, because there's a bunch of pitchers and stuff in here. Okay. We can use multiple columns, which is pretty cool. So this is an interesting, so if we want to know about a player's acuity as running the base paths, we might want to know about stolen bases and how many times they were caught stealing. So an attempted stolen base that was unsuccessful. And so what we might want here is the descending order for stolen bases and then the ascending order for caught stealing. So we want to know the guy with the most steals and the fewest caught stealing if they're tied. And so we sort by stolen bases and caught stealing, and then the sort index is ascending, false on the first one, true on the second one. And so we get Gary Sheffield, also former Atlanta Brave. Okay. Slightly, related but different, the rank. So ranking does nothing to your data. It simply returns a statistic, which is its rank within the data set. And you'll notice there are somehow floating point numbers here, and that's because there are ties. And if there are ties, it takes the average among the number that are tied. And just to see this explicitly, if you take two values and you do the rank of them, it's 1.5, because it's the average of 1 and 2 for both. And you can specify ways of breaking those ties other than averaging, like it can give the one that was encountered first the highest rank or the lowest value, and the second one the second, and so on. So if we do that, suddenly we have no floating point numbers because everybody has a unique rank. DataFrame has a rank method. So everything from highest to low, or lowest to highest, excuse me, starting with the first column and working its way over. So it uses each successive column to break the tie from the previous ones. Okay, it's maybe a little easier to see if we only look at a couple of columns. Okay. What I'm going to do now is do an exercise break. So you can do this exercise if you want some hands-on, or take a break. So I'll give you like 5-10 minutes to do that. So this is on-base percentage. So this is another one that's sort of complementary to slugging. It's how often a person gets on base. So hits, walks, hit by pitch over all of your at-bats, your walks, hit by pitch, and sacrifice flies. And if you get both slugging and on base, you can calculate an OPS, which is seen a lot in baseball. So yeah, maybe 5 minutes if you're going to get a coffee or go to the bathroom, and give you 10 minutes to do the exercise.